So in this video, I want to review bitwise operations on integers. So first I'll go over these four operators. And for AND, when you AND two numbers together, the resulting number is only 1 if the bits of the two original numbers are 1s. So in this case, these are both 1s, so the final bit is 1, but otherwise they're 0s. And for OR, the bit of the resulting number is only 1 if there's at least if the bits of either of the two original numbers are 1. So that would be in the first, third, and fourth place here. But in the second bit here, they're both 0s, so the resulting bit is 0 for the second place. For XOR, the final bit is 1 only if the bits of the original numbers are different. So in this case, for the first and third place, the bits are different, so the final bits will be 1. Otherwise, they're 0. And then for negation, you simply flip the bits. So if they're originally a 1, they turn into a 0. And if they're originally a 0, they turn into a 1. So now I want to go over left shifting and right shifting. So for left shifting, you just move the bits to the left, and then you fill in the empty spots with 0s on the right. So for this number here, if I want to left shift twice, I move the bits to the left twice. So the first one will end up in the third position, the second one will end up in the fourth position, etc. And then I just fill in 2 0s on the right. And for left shifting, it's the same. If you left shift a number, it's the same as multiplying the number by 2 to the power of how many times you left shift. So for instance, in this case, I left shifted twice, so it's the same as multiplying the number by 2 squared. And you can see because the original number is 7, and when I left shifted it, it ended up being 28. So for right shifting, it's pretty much the same, pretty similar to left shifting. And also one thing to note for my examples, I'm assuming integers are 5 bits. And obviously it's different when you're programming. When you're programming, the integers are usually 32 bits. But for simplicity, I'm just using 5 bits. So for right shifting, you just move the bits to the right, and you want to copy the highest bit for the empty spots. So for instance, if I want to shift this number here, I move the digits to the right twice. So the third 0 will go to the first position. The fourth 1 will go to the second position. And then these 2 1s here will just be deleted. And then for the 2 empty spots on the left, I want to copy the highest bit. So in this case, the highest bit is 0, since it's a 5-bit integer. So I just put in 0s here. And if I look at this number here, if I want to shift to the right twice, I shift the numbers, but in this case, the highest bit is 1. So now I want to just put 1s in the 2 empty spots. And the purpose of copying the highest bit is to keep the numbers in the correct sign. So if I shift a positive number, it'll keep it positive. And if I shift a negative number, it'll keep it negative. For right shifting, it's different from left shifting, as since now you're dividing by 2 to the number of times you shifted the number, but you're also rounding down to negative infinity. So in our top example, we originally had 11, and when we shifted right twice, we divided by 2 squared. So 11 divided by 4 would be 2.75, but you're rounding down, so it'd be 2. And similarly, for negative 11 in this case, in our second example, when we right shifted twice, we divided by 4, so that would be negative 2.75. But then you round down to negative infinity, so then you round to negative 3. So now I'm just going to quickly go over a practice problem that I think ties up the concepts of bitwise operators pretty well. And the problem is we want to find a function that can get the middle 4 bits of an 8-bit integer. So for instance, we have an 8-bit integer here, and then we want to return 1011, since the middle 4 bits are right here. So in order to do this, we have to think, okay, we somehow have to extract these bits. So we know that we don't care about the last 2 bits or the first 2 bits. So what we can do is first AND the original number, which is this, with this number. And when we AND it together, for the ones, they keep the bits as they were. So for 1011, when you AND it with all ones, it'll stay 1011. But for the last 2 bits and the first 2 bits, if you AND it with zeros, it'll just turn those bits into zeros. And that's good because we don't care about the last 2 or the first 2 bits. And then after we AND it, we can't just return this number. We have to somehow move these bits to the front, which we can do with the right shifting. So now we can just right shift the number by 2, and then we get this number. And now this is good. We can just return. So to visualize this function in code, if we have a function called get middle 4 bits, we want to take in the number, and then we want to AND with this. We want to AND it with this number here. And in my code example, I just turned it into a hexadecimal. So this number is the same as 3C in hexadecimal. So we AND it with 3C, and then we want to right shift by 2. And then we can just return it. And note that you could also right shift by 2 and then AND it with like another hexadecimal number. It doesn't really matter. But also remember that for this example, I'm doing it for an 8-bit integer. But usually when you're coding for C0 in example, you will be coding in 32-bit integers.